Welcome back to the live classroom again. We've been talking for the board examination for the grade 12 students. So I would like to mention a few more points about the questions. Concept related to what we have discussed before the break. One question was about concept related to magnetism, and one question also we have discussed related to magnetism. Right, and now I would like to about optics. That's about lens maker's formula. Okay, a concept about lens maker's formula we will see. A few points or a few questions as well related to that we will see. The equation that you are familiar with is 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. 1 by r1 minus 1 by r2. Lens maker's formula. And what we have observed is the refractive index of the second medium with respect to first is what is that is this is n21 is what you write as normally n2 by n1. So be very clear about this point. At this point be very clear this aspect, like n1, that is whichever is the denominator, whichever is coming in the denominator is the refractance of the medium in which the lens is kept. Two refractive indices are mentioned here. One is N2, which is the refractive index of the lens, whichever be the material of which of which the lens is made. That is the refractance of that medium. That material is N2, and N1 is the refractance of the medium in which it is kept. For example, a normal glass lens, when it is kept inside water, N2 is supposed to be the refractance of the glass, and N1 is supposed to be the refractance of the water. Why I'm stressing this point now is because sometimes in the exam they will give you the other way. N1 is that of the glass, and N2 that of the medium. Then you should change it to N1 by N2, and it should be N12 it is supposed to be. Okay. Anyway, be very clear. N2 is the refractance of the glass, and N1 is that of the medium. So this equation, when you use it for a convex lens, that is this lens, how will this form the equation become? This equation becomes, this radius of curvature you might have seen. If you consider the light rays coming from left this way, then the radius of curvature of first surface is positive. It is in the direction of the incident ray, so it is positive by sign convention, and the other radius of curvature is negative. So R2 becomes negative, R1 becomes positive. So if given case of convex lens, so R2 is negative of negative, so this equation becomes 1 by R1 plus 1 by R2. Be very clear. If so, in the question wherever you are going to use lens maker's formula, you check what kind of lens it is. If it is convex lens, the equation should be in this format: 1 by R1 plus 1 by R2. Okay, 1 by R1 plus 1 by R2 is one thing. The next thing is, like, this is how the refractive index we are writing. Okay. So the next point is two different situations we take into account. Normally, when a glass is placed or glass lens is placed inside in air, or if it is placed even inside water, the refractiveness of the glass is usually greater than that of the medium around. Refractiveness of the glass is usually greater than the medium around. So medium's refractive index is usually less. That means usually what's the picture? The refractive index of the second medium, that is of the lens with respect to the medium, will always be greater than 1. This is usually happening. Why? Because the refractive index of the medium is usually less. So this is bigger than 1 means this part will always be positive. Okay, this is greater than 1, so this part is positive, and this is anyway positive into positive. So focal length is, for a convex lens, usually the focal length is positive. By the way, what do you understand from positive focal length? You see, light rays coming like this will converge to a given point. See, if the light rays converge like this, the focal length we consider is in the direction of the incident ray, so it is positive. So be clear, positive focal length indicates the lens is converging. It's a converging lens. Understood? Positive focal length indicates the lens is converging. So what we understand therefore from this, normal situations a convex lens is a converging lens, because normal situations a convex lens in the case of convex lens, this is satisfied. So this is positive, 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 so it will become positive only. It is positive. So focal length is positive. So what we can make out, since focal length is positive, it means the lens is converging lens. Now the question, is there any situation the focal length can be negative? Otherwise, is there any situation when can focal length be negative? Focal length is negative. You think of the case the other way, that is medium has in the first case medium is considered to be less refractance. In the first case this is medium's refractance is less than that of the glass. But now if it is the other way, that is medium's refractive index is bigger, then what happens? N1 is bigger than N2. So this N21 becomes less than 1. So if this becomes less than 1, to make a correction the previous section, it was the other way. Okay. So if this is less than 1, if it is less than 1, what you can make out is this will become negative. If this is less than 1, this becomes negative. If this is negative into positive, it becomes negative. So focal length becomes negative. Focal length negative indicates the lens is diverging lens. Even if the shape of the lens is like this is convex in shape. But when light rays coming like this in this picture, in this situation, that is if the refractive index of the medium is higher than that of the lens, then what happens is it will go like this, it will diverge away. So now an important question comes this way: can a convex lens behave as a diverging lens? Usually when we say convex lens, it is converging only. So can a convex lens behave as a diverging lens? Answer is yes, when the lens is immersed in a medium of higher refractive index. When the lens is immersed, that is medium's refractive index is more than that of the lens. So when the lens is immersed in a medium of high refractive index, a convex lens can even behave as a diverging lens, diverging. Okay, convex lens is diverging. Is it clear? So by the way, in questions of this sort, whenever you are asked to calculate focal length, sometimes question follows would be, what's the nature of the lens? Nature of the lens. When you talk about nature of the lens, it is not correct. It is not correct to say convex or concave. When you are asked to write the nature of the lens, you should say converging or diverging. This is the reason. Because if you say convex lens, it doesn't in fact represent the nature. Nature means what? Convex lens can even be a diverging lens also. So what is the conclusion? Let us conclude this way. A convex lens is normally converging. Normally means if the refractive index of the medium is less than that of the lens. That is a normal situation. That like when lens is placed in air, there the lens is converging. Whereas if the refractive index of the medium is bigger, say a typical example is there. Glass refractance of glass is how much? Nearly 1.5. Average refractance of glass. And that of there is a substance called carbon disulfide, CS2. Its refractive index is 1.6. That means if the normal glass lens is immersed in carbon disulfide, the behavior will be opposite. Convex lens will behave as a diverging lens like this. Can you say what happens if the medium has the same refractive index? That is, I am changing it to N1 is equal to N2. Then what will happen? These two are equal. That means N21 becomes 1. So this part becomes 0. This is 0. 1 by f is 0 means what? 1 by f 0 indicates focal length is infinity. Infinite focal length. Infinite focal length means if the light rays are coming like this, it will go like this. It will not deviate. It will go straight. That means as if it is a plain glass plate. So once again, convex lens normally converging. That is if the medium's refractive index is less. Can be diverging if the medium has a higher refractance than the lens. Can even behave as a plain glass plate when if the medium's refractive index is the same as that of the lens. Is that clear? However, if it is like the case of diverging concave lens, if you take into account, it will be just the opposite way. If it is concave lens, this is the normal equation I said. If it is a concave lens like this, what we have to see is concave lens, this radius of curvature is negative, that is this is negative, the other one is positive. So the equation for a concave lens comes like this, lens maker's formula. Okay, equation for a concave lens comes this way. So if the equation is in this way, you see this part is normally negative. Normally negative means the lens is normally a diverging lens. Normally it is negative. Because this is negative, this is normally greater than 1. But if it is placed inside a medium which is having a higher refractive index than the lens, then what happens, these light rays coming will, instead of diverging, it will behave as a converging lens. Even converging lens it can be. Why? Because this becomes less than 1. So this becomes less than 1, so this becomes negative. This term becomes negative, negative into negative, so it becomes positive. Right? So focal length positive means lens behaves as a diverging lens. Sorry, the lens behaves as a converging lens. Right? Concave lens can behave as a converging lens. Even if they are equal, it will behave as a plain glass plate also. So let us sum up all these points together like this. Convex lens normally converging, concave lens normally diverging. Convex lens can behave as diverging if the medium's refractive index is higher. In that situation, concave lens will even behave as converging. And both concave and convex lenses, they both will behave as plain glass plates if the medium's refractive index is the same as that of the lens. Okay, so from lens maker's formula, one more thing we can make out is, I'll explain one question. Question is, what's the situation or what's the condition when the focal length of the lens, convex lens, there are, we use the term equiconvex lens. Equiconvex lens means the lens which has got the same radius of curvature, that is R1 and R2 both are the same. So for an equiconvex lens, what would be what's the condition for the focal length and radius of curvature to be the same? Meaning, so for a concave mirror or for a mirror generally what we have is, for a mirror we have the equation radius of curvature is twice the focal length. But remember, the radius of curvature is 2 times the focal length is applicable only for mirror. But for a lens, let's think of this aspect. I said for a convex lens we have the equation refractive index is 1 by f is equal to refractive index of glass, simply writing glass means absolute refractive index, that is with respect to glass, minus 1 into 1 by R1 plus 1 by R2. 1 by R1 plus 1 by R2. Okay, so if it is equiconvex lens, suppose we have got an equiconvex lens of refractive index 1.5, that is, it is given refractive index of the glass is 1.5. Okay, so 1.5 minus 1 into, imagine both of them same radius of curvature, that is equiconvex lens. So 1 by R plus 1 by R, which is 2 by R. Okay, so it becomes what? 1 by f is equal to 0.5 into 2 by R. It's fine. So what we can further make out is 1 by f is equal to 1 by R. Therefore, f is equal to R. So focal length is equal to radius of curvature. So what we have seen here? If the lens is an equiconvex lens of refractive index 1.5, the focal length of the lens is equal to the radius of curvature. That is one thing to understand. Okay. Once again, a mirror, in the case of a mirror, radius of curvature is twice the focal length, that we have seen. But in the case of lens, the radius of curvature and focal length can be the same if the conditions are there. One is it should be an equiconvex lens. Second is its refractive index should be 1.5. So once again, what's the conclusion? For a lens of refractive index 1.5 and having the same radius of curvature on both the surfaces, focal length and radius of curvature are the same. One more question I'll tell you. when a lens is cut into two equal halves. So this I'll give you one question for you to try, and we will see actually in the next week, this week itself, coming Wednesday, we will have again one session, the same thing, board exam. So by the time all of you can, because tomorrow you have English exam, you might not be able to have the preparation today. So tomorrow onwards, when you start preparing, whatever doubts you have, you keep collecting, and tomorrow, on Wednesday at 5 o'clock, we will have a live session. So if you have any doubts, you can call. And again, this is the question which I am giving you to solve, and keep the answer with you. You can say what's the answer. So first of all, this is an equiconvex lens of focal length f. If this lens is cut into two equal halves like this, what's the focal length of each half? Suppose f dash is the focal length of one half, like this, one half will come like this. What will be its focal length? So once again, what's the question? An equiconvex lens has a focal length f. When it is cut into two equal halves in this manner, what would be the focal length of each half? So try that question. And again, questions related to lens makers formula, you'll have to keep working out. There are questions like calculate focal length of the lens when it is immersed in water and things like that. There are questions of that sort. So you keep practicing, and based on the board examination, or in the light of the board examinations, we are going to have one more session on physics itself this week, Wednesday. So all of you, or if your friends are also, they are writing the examination, so you tell them that we'll have a session, live session, so that you will be able to ask your doubts in the last phase of your preparations. So hope the English exam is going to be very easy for you, and wishing you very best of luck to all those who are going to write the exam, board exam tomorrow. Let me wind up today's class. Have a nice day and have a nice examinations.